All right, so we're going to change internal energy, and let's concentrate on the way we can change internal energy via changing the temperature of the object, so therefore speeding up the particles. Obviously, different objects, you know that from common sense, everyday life, different objects heat up differently. Their temperature changes differently. And the amount of energy that you need to invest into bringing the temperature up depends on three things. It depends on the mass of the substance. The more the substance, the higher the mass, the more molecules you're dealing with. So therefore you will have to excite more molecules and invest more energy. Obviously it also has to do with how different you want the temperature to be. So per every degree of change you have to move to invest more and more energy. And then obviously it also depends on the substance itself. So mass and the change in temperature are kind of universal. I mean, you can measure mass, you can measure temperature, but the substance itself, like what do you mean by substance itself? What happens there is we look at what is called specific heat capacity. Specific heat capacity, you can just think how much energy you can pack into the object in order to bring its temperature by 1 degree, and that will happen to 1 kilogram of substance. So for example, if you look up the specific heat capacity of aluminum, it's going to be 899 joules per kilograms per Kelvin. What does that tell you? That if you have a kilogram of aluminum and you want to raise its temperature by 1 degree, whether it's Celsius or Kelvin, it's the same. Remember, change in temperature in kelvins equals change in temperature in Celsius. So let's say I had a kilogram of aluminum at 22 degrees Celsius and I want it to be 23 degrees Celsius. I need to invest 899 joules of energy. What if I don't have a kilogram? What if I have less? And what if I want to change the temperature differently? So I will still use, in order to figure out the Q, I will use CPm delta T. So CP is 899. Mass has to be in kilograms, so therefore 0.55. And the change in temperature, my final is 25, my initial is 20, so I subtract 25 minus 20, I get 5. And that gives me 2,472 joules of energy. That is how much energy I need to invest into aluminum, specifically 550 grams of aluminum, to raise its temperature from 20 to 25. I would have had to spend just as much energy if I wanted to bring it from 25 to 30. All that matters is the change in temperature, not the actual T, whatever it was. All right, so I looked at the energy just supplied by something. I didn't really care where that energy comes from. What if I know that my energy came from work done by friction? So I had mechanical energy and it turned into internal. So here's an example. 1,200 kilogram car is moving at a speed of 32 meters per second, and 75% of its kinetic energy turns into internal energy of the 4 brake discs. Each brake has a mass of 3.2 kilograms. So my question is, how much will the temperature of each disc change? And I'm giving you a specific capacity of that material that the discs are made of. So 75% of kinetic energy of the car turns into its internal energy. Not just its internal energy, but the internal energy of the brake discs, because those are the places where your friction is taking place. That's where friction is working. And so 75% goes into discs and the other 25 go into tires, air, and whatnot. So how do I find kinetic energy of the car? mv squared over 2. And Q for the discs is going to be CP of the material. 4 discs, therefore I'm multiplying mass of each disc by 4 and find change in T. So therefore 75.75, which is 75% mass of the car, V squared over 2. That's from kinetic energy formula, and then 4 masses of discs. So that, and when I put all those numbers in here, it will give me 80 degrees Celsius. So what we had here, we had mechanical energy of the car because of the work of friction turned into internal energy of the brake discs. And we just, instead of Q as Q, we knew that Q was 75% of kinetic energy. So that's another way of doing it. How do you find CP? Like, we know CP of different materials. I just gave you 899, but how did they figure it out to begin with? What happens is we use a calorimeter. Why do we call it a calorimeter? Because it just happens that 1 calorie is 4.8, actually it has to be 186. Ooh, oopsie daisy. So this has to be reverse. 4.186 joules is 1 calorie. 1 kilocalorie, or the capital C calorie, is 4,186 joules. What does that remind you of? Hopefully of something, and that something is specific heat capacity of water. So it's called calorimeter because number one, it measures the amount of energy which can be measured in calories, but it also uses water in it. And specific heat capacity of water has to do with a calorie. So what calorimeter in the nutshell is, it's a container which is insulated to prevent energy loss, and you fill it with water, and you put a sample, so it's filled with water, a sample, and after some time, sample has to be hotter than water, and after some time what you see is the temperature of water is going to be increasing because energy will flow from the substance into the water. So here's your Q. It's the exchange of energy between the hot substance and the colder substance. So the way it's done, you need to measure 5 things. You need to measure the mass of water, the mass of the sample, initial temperature for both, and after you stir this up, provide convection and mix up and let them reach what is called thermal equilibrium, you will register the final temperature for both. And then, since if we're an ideal world, our calorimeter is absolutely insulated, there's no energy loss, then I can say for sure that the Q of water plus the Q of sample is 0. Q of water, water is going to warm up. Temperature of water is increasing. So Q for water is positive. The temperature of the sample is going to decrease. So I can say that the Q for the sample is negative, plus, minus, add up to 0, therefore. And so I can say Cp of water, mass of water, change in temperature for water, not for the sample, for water. And then Cp of the sample, mass of the sample, and again, change in temperature would be for the sample, not for the water. What if energy is lost? Well, then you have to account for another Q of the loss of energy. There could be an example where instead of Cp, you would be asked to find T final. So which would be given? You would be given all of that and all of this, but you would have this T final to find minus your T initial of water, and then you would have T final again, which you're looking for. It's the same for both of them, minus T initial, T initial of the sample, and then you distribute and rearrange, or if you know the shortcut, you could take the shortcut. But anyway, you would still have your Q plus Q plus Q plus Q plus Q all equals 0, even if there is energy loss. All right, phase change. That's going to be our next topic. So phase change, it takes place after you have excited those molecules so much that they cannot move any faster without breaking the bonds between them. So if you had a solid and you heat it up to what is called a boiling melting temperature, it will turn into liquid if you keep adding energy. If you had liquid and you subtracted energy, if you removed energy, it will condense and turn into solid. If you had liquid, it can also turn into gas if you add energy, or if you have gas and you remove energy, it will turn into liquid. So it's just the phase change, as in solid to liquid, liquid to solid, solid to, liquid to gas, gas to liquid. A change of state, in other words, and it takes place at a constant temperature and a constant pressure. So if the temperature is constant, but you're adding energy, where is it going? If temperature is constant, that means that our molecules are not moving any faster. Kinetic energy of those particles is not changing. But where does this go? This added energy is definitely turning into internal, and remember, internal energy is comprised of kinetic energy of particles and potential energy of particles. So potential energy of particles is increasing if you're putting energy. That means that they're moving farther apart, like when you're going from liquid to gas. They're really, really spreading out. Let's look at This would be the phase change for, the graph including phase change for water. So let's say we started with ice. If ice was initially at negative 25 and you start putting energy in, first it will heat up to 0. So this right here is going to be an incline, and as you see, the incline means that there is change in temperature. It went from negative 25 to 0. Since there was a change in temperature, you will do Cp m delta T, and you will use Cp for ice, because right now that substance is ice. Then you hit plateau, which means that now, even though you're investing energy, that energy is going into potential energy of the particles. It's melting. Particles are moving farther apart. And then if you look over here, if I were to find the Q for just melting, that would be the difference between 385 and 0.522. Then, once I melted the entire amount of ice that I had, if I keep putting energy in, now I have water, and those molecules are going to start moving faster, and what I will see is the change in temperature. So the temperature is going to rise, and at a normal atmospheric pressure, at 100 degrees Celsius, those particles will not be able to move any faster. So what is going to happen? We're going to hit another plateau. And there you go. And then potentially I can vaporize everything and then turn it into vapor and then heat up even vapor after that. So what do you need to do with phase change problems? First of all, analyze what processes are taking place. Ask yourself, is the object at the melting point or is it at the boiling point already? So the added Q, will it go into melting or boiling? If it's not, then you need to figure out how much energy is required to bring it to the boiling point. And then just add all those Qs, and that's it.